So last time, what we did in the introductory lecture on objects that move through resistive media was to look at forces that affect the motion of such objects. And we encountered two forces, and these were drag force and lift force. And for simplicity, we decided to take the lift force as 0 by employing some assumptions. So in examples we'll consider, we don't need to worry about the lift force, but we will take care of drag force when we think about objects moving through a resistive medium. So this is a small recap of the material that we went through. So remember that there were two types of laws that we picked up from the analysis of drag force, which came directly from dimensional analysis. And we had the following. So assume that we have an object. It moves with the speed v in a resistive medium. Then there is a linear law of resistance which describes the drag force experienced by the object. If the fluid has the fluid has a low Reynolds number, is characterized by a low Reynolds number. So here the magnitude of the drag force, this is magnitude, is equal to some constant which you have to find experimentally, multiplied by the speed v of the object. Now, if you do some dimensional analysis of the problem, so in other words, time to look back at week 1, when we started the module, you'll see that the drag force has to have the units of m, l, so that's m for mass, l for length, and t for time to the power of minus 2, okay? Now, they are in SI units, this means we have kilograms, meters per second squared. Now, we know that speed is the magnitude of velocity, but in any case, it has the units L times t to the power of minus 1. So if we look at our equation here, if we look at our equation, we can determine, as we had done a few times with the different examples in the first week, we can determine how we can get hold of the units for B. In fact, on quick inspection of just trying to make this equation dimensionally consistent, we see that the constant B has to have the units of mass per unit of time. Okay, so that when we multiply these two together, we do indeed end up with ml t to the power of minus 2. Now, what about the quadratic law of resistance? Well, we say this holds for sufficiently high Reynolds numbers. So that's a fluid that is characterized by this property, this constant, the Reynolds number. Now, in this case, what we have is the magnitude of the drag is equal to some constant, again, multiplied this time by the square of v. This is different constant to the formula above now. So this is a different constant. And again, we can do some dimensional analysis of this, and we can compare left with right. So we know our left-hand side is this. We know our v as the units L t to the minus 1. So we know that the square of v should be L squared t minus 2. So again, if I just look at my equation for the quadratic law of resistance, what we see is in order for this to be dimensionally consistent, we should have B having the dimensions equal to m times L minus 1. Okay, so that is so that when we multiply this one, when we multiply, let me go back a step. When we multiply these two together, you'll see that the the drag force, the magnitude of the drag force, the units of this force are recovered when we multiply v squared by b. Okay, so before moving on, we're going to just take a look at an aside note. So this is an aside note. And what we'll do is we'll consider a stone moving vertically through the air. Through the air in the absence of gravity. Of course, this is generally not true, but just for argument's sake, we'll consider this, because really what I want to do is I want to highlight something concerning the linear law of resistance. Okay, or using the linear law of resistance, I'd like to just highlight this comment. So we have, say, a reference system. So we're used to these things when we looked at the introduction to dynamics. So my vertical is vertically up is positive y, and I have a stone moving up through the air. Okay, its motion is this way, and I can say that my velocity vector v for this is equal to the following: v of y of t. So motion upward. V of y of t, so vy is a function of t. So that's my velocity. And what I can do is I can say, all right, I have the modulus of v is the speed, which in this case is vy. Modulus of vy. Okay, and this is a vector on the left. Now, because this stone moves upwards in my positive direction, according to my reference system, is vertically upwards, then this thing here, if my stone's moving upwards, is positive. Okay, can be positive, can be negative, but in this instance, when it moves upwards, it's positive. Of course, when it's coming back down, this is a different story, and this Vy has to be negative. Okay, so let's assume, and we'll look at this case in a second. So let's assume that we encounter air resistance. Now, air resistance will give a resistive force as the stone tries to air resistance. As the stone tries to move upwards, it gives a resistive force to the stone that opposes the direction of the motion. Okay, so in other words, there is a force now due to drag. This is the drag force. I write it as vector d, Fd, and we know this has magnitude F equals, magnitude, that's the vector itself. We know that this has the magnitude using linear law, for instance. It has the magnitude, let's take a look, so B times the absolute value of our vector v, which is b modulus vy of t. Okay, so knowing this, I can indeed now construct the vector fd, which acts in the negative y direction. So fd as a result is the following. it is minus b times Vy j. Now, minus y, because as we've done in countless examples beforehand, this force opposes the motion, and in this case, if the object moves upwards, the force acts downwards, the resistive force to drag. Okay, now I'm going to go a step further. And I'll write this as minus b. Now remember that this thing, Vy of t, is positive, so what we have is just this. Okay. Now, good. So what happens then if we have the same case, but now the stone moves vertically downwards? Well, I'm still going to keep the reference system pointing upwards for positive. I now have a stone, the same stone, so let's assume it's reached its maximum height. And then it begins to fall down, okay, for whatever reason. I know I haven't put in gravity in this case, but let's assume it's on its way down. So this thing has, of course, again, velocity Vt. And so this is on its way down, and we know now that this Vy should be negative. Let's actually write the symbols for this just to save space. So this should be less than 0. Okay, now, in this case, the drag force due to the air resistance again opposes the direction of motion. So Fd is the force that acts up. We know that this has the magnitude B modulus Vy Ft. Okay. Except this time now, Ft is going to be given if I want to actually write the vector, because remember, if we're talking about Newton's equations of motions, I need to write vectors. The vectors have to have the correct signs, so I need to be able to construct these in the right way. So if I know the magnitude, I know this Fd points vertically upwards, so it is simply this without now the minus which we had before. So this is the now our drag force factor. But I can go one step further. Remember that this is negative. This is negative. So I can write this as minus b Vy, taking out the modulus, because the minus in the Vyt is positive. So one thing to note here, by the way, here B is positive in all of this, because I was talking up here as we are discussing magnitudes. So if you're wondering, well, what about this B and the forces I've just talked about? Well, it's positive, so we don't have to worry about this changing the sign of anything. So therefore, what I have is that's my drag force on the way down. And you will see, just by comparison, you will see that the force on the way down, the force vector, which represents the air resistance for an object on the way down, actually is the same as that for the object that moves on the way up. Therefore, so let's call this double star. Let's call this star. Star and double star show Fd, the drag, whether it moves up or down, is always this, minus b Vy Tj. Again, whether regardless of moving up or down. So that was the aside note. Okay, that's the message behind this. So when we think of drag force in future examples and use the linear resistive law, we'll just write in this. Okay, this will be our magic formula. Okay. Okie dokie. So what we need to do now is we need to do some examples. So in this example, we have a ball bearing placed in oil. Ball bearing placed in oil. Very important piece of information, because this is actually telling you what you should do as a low Reynolds number. Model the motion of the ball bearing in the oil. So the oil has low Reynolds number. This ball bearing is falling through the oil. So we're told if it falls through the oil in a straight line downwards, what's the maximum speed the ball bearing reaches? Okay, so this is, imagine this is our oil. Oil. And this is our ball bearing. Okay. And it's falling down. Let's suppose this is the level, the top of the oil, and Y. Now I'm choosing our reference system so that Y points downwards. So here, it was released here. This was its initial position. For the ball bearing, released here. Y equals Y of t. Y of t when t equals 0 equals 0. Okay, in other words, i.e. y of 0 equals 0. That's our initial condition. Also, v of 0, because it was released from rest, we're going to assume release from rest. So v of 0 is 0. Okay, so what is going on? Well, we have the motion going downwards. I have two things going on. So let's put on arrows that represent forces. So we have a force representing action of gravity. Gravity force. And then we have another force which, due to the low Reynolds number, we will have a linear drag force. So drag force, which opposes the motion. So drag force, we're going to need to calculate this. Gravity force, and then we're going to need to sum them up. Why? Because remember that using Newton's equations of motion requires a net force, a resultant force. So we have drag force. Now, low Reynolds number. Implies linear law of resistance. Just take that down. Okay, so the magnitude is B, V. So what, V of t? That's the magnitude, which is BV of t, because here this is positive as ball bearing falls. interaction of positive y. Okay, so knowing this, my Fd is, of course, a force that opposes the motion according to the diagram, so I need this. Okay, using techniques that we've used before in the introduction to dynamics. So what about Fg? Well, our old friend is magnitude mg. This is mass of bearing, and this is acceleration due to gravity. So Fg is the following. We know it as magnitude mg. It's a vector that acts in the vertical direction. Additionally, it acts downwards, so it has the following form. Mg. Why? Well, because mg is acting, so this is plus because acts in direction of positive y. Okay, so what we need there, we need the net force for Newton's second law, so net force or resultant force. We need this F, which is just Fd plus Fg. And if I sum these two together, what I get is mg minus bv. Right, so if I know this, then my Newton's equation of motion asks me, well, give me the net force. So I have m dv, velocity by dt, equals f. Now here, just going back up to the top, remember that v, the vector, is, I'm using the notation v without underscore to represent our velocity. That's our velocity vector. Okay. So if I plug everything that we know in, what I get is the following. I get m dv by dt j equals mg minus bv j. Okay, so a basic argument from analysis of vectors tells us these two guys on the left and the right are only equal if the components of the vectors are equal. So this tells us we have the following. We have the ODE, the differential equation. Okay. M dv by dt equals mg minus bv. All right. Okay. Now, well, what about that? Well, now we just need to solve it. Solve this and use initial conditions. So, what do we do to solve? Well, you can do one or two things. Integrating factor method. I've shown you quite a number of times how to do this using the separable method for separable equations. This is indeed separable, so I'm going to do this. Okay, separable equation. So if I just rearrange for a second, so step one, rearrange. To have function of v. on right hand side with the derivative. Oh, sorry, on the left hand side with derivative. Okay. So if I just do some manipulations first, m times dv by dt, if I factorize out on the right hand side, if I factorize out minus b, what I have is v minus mg over b. And then what happens is I can divide by this factor, so divide by this. For how can I say, ease in calculation, I'll divide also by m. Okay, so what we get is, after this, we get dv by dt. 1 over v minus mg over b equals minus b over m. And then we're in the scenario where all we have to do is just integrate. Now integrate with respect to t. So what I get is this. Now, on the right hand side we have constants. So I'm just going to take them outside. This we know after 1 million times is just dv by chain rule. This here on the right, well, that's just really easy because it's the integral of 1. So I don't no need to underline that. Just move to the next line. So we have integral v minus mg over b dv. So that's an integral of a function of v minus b m t plus c, and this is arbitrary constant of integration. So this is arbitrary constant of integration, and we can find this using initial conditions. Okay, so this is what we'll do. So what do we get? Well, I'm taking this now. So the next step, I'm taking this equation, and what we can do is now integrate left hand side, rearrange for v. Okay, so left hand side is just logarithm of the modulus of mg over b. So this is this. Then I'm doing rearrange. So to do this, I just take exponential of both sides, standard stuff. Now I'm writing this in the following way on the right hand side. Now to do the modulus, I have to keep in mind that this can encapsulate plus or minus the right hand side. This we'll call a new constant a, doesn't matter. So v equals a e minus b over m times t plus mg over b. Now, find a using initial conditions. So v of 0 equals 0. That was our initial condition. So using this, I have, therefore, this is as a result of our initial condition. Then if we plug in star, what we have is a e to the 0, which is just 1 plus mg over b, So this just implies that A is minus mg over B. And so solution is V of t equals, now I'm doing some simplification, 1 minus this exponential term. Ta-da! Okay, so with this in hand, that's our solution. So we were asked to find what the terminal velocity is. Remember that this is monotonically decreasing function. Why? Because m and b are greater than 0. If I draw the graph of the solution, it looks something like this. T, of course, we start where t equals 0, we start at 0. And then, as we increase with time, the size of this exponential term will just become smaller, so we get something like this. And we approach an asymptote, a horizontal asymptote. This horizontal asymptote corresponds to mg over b. Okay, so if I want to know the maximum speed reached, so max speed is just found from taking the limit as t tends to infinity of v of t, which just gives us, using standard rules, mg over b. So that's the max speed of the ball bearing as it drops through this barrel of oil. Okay, so that is everything for this example. Hope you enjoyed it. See you next time for the next example. Thank you.